But without indulging further, I let the floor to Adam.
Thanks. So yeah, this, as Francesca just said, this is a joint work with Chris Smeenk. We're looking at theory of inflation and what kind of is needed still, what we find lacking with the theory of inflation right now, and what we think is needed, and some helpful suggestions for how to establish a theory of inflation. So this is a more general philosophy of science programmatic talk. I'm interested in issues of theory construction and theory confirmation, and so that's kind of using inflation to think about those issues. So just a quick summary of what I'm going to talk about. I'll go over the introduction quickly. For us, very helpfully already talked about inflation, so I don't need to cover much. I'm going to argue that inflation right now, the sort of standard way it's thought about, is as a sort of phenomenological framework for capturing details of the early universe. I'm going to argue that that is unsatisfactory, and that there's sort of a couple ways you could choose to go forward to sort of make it something more than phenomenology and a sort of physically robust theory, one of which is to think of it as an effective field theory. As you probably gathered from the morning, I mean that in a slightly more robust sense than Faraz does, so I don't think anything I'm saying disagrees with him, but I'm going to say that effective field theory doesn't really work for getting that extra sort of level of establishment for inflation. Then I'm going to think about what sorts of things you can't do with just a phenomenological theory and what we'd want more for inflation, and then some steps towards how we might go about shoring up the sort of foundations of inflation. So what is inflation? As Faraz mentioned this morning, we have a speculated period of very rapid near exponential expansion of the scale factor in the early universe. It's very model dependent on exactly when inflation starts and ends, but somewhere very briefly after the Big Bang, sometime after Planck time. The standard canonical approach is to think about inflation as being driven by a single scalar field, though there are generalizations of that. You have multi-field, you can have the framework that Faraz outlined that goes in more general ways, but that's sort of the standard thing that I'll have the scalar field version in the background here. It's currently, right now, there's many different ways to realize inflation, so you can think of what's common to all of those as a sort of framework, or like a sort of framework for a mechanism, rather than any particular model of inflation. So that's what it is. Why do we think, why would we bother positing inflation? I think its main appeal is as an explanatory mechanism. It's not so much that it predicts new things about the world, or like the observations have forced us to this thinking that inflation must have happened. It provides explanatory depth in a way that Faraz outlined this morning as well, in particular in addressing the horizon and flatness problems for the hot Big Bang model, and providing a mechanism for structure formation. So the horizon and flatness problems, again, quick summary. This is covered before. Basically, they're fine-tuning problems with the standard hot Big Bang model. They take different forms, but they're kind of puzzling features that we have to sort of just posit special initial conditions for the hot Big Bang. And that's sort of unsatisfactory because, so for flatness, for example, standard dynamics, if you're not exactly flat at the initial conditions, the standard sort of cosmological evolution will drive you away from flatness. So given that we observe the current universe to be very nearly flat, and if we just extrapolate backwards using the dynamics without inflation, that would lead us to have to posit initial conditions that are sort of very, very, very narrowly chosen. They have to be almost exactly flat to very high degrees of precision. The horizon problem is just that we observe from the cosmic microwave background that the universe seems to be in pretty near thermal equilibrium. If you take standard cosmological dynamics without inflation and evolve back, those regions that are at thermal equilibrium would have never been in causal contact in the past. They extrapolate back to the Big Bang. Those things would have never been in causal contact. So it seems puzzling that they're all in thermal equilibrium. Again, as Faraz mentioned, these aren't problems of empirical adequacy with the hot Big Bang model, you can just, if you postulate the right initial conditions, you get this out. So these are just more puzzling features that we think, that seems odd that our universe had to have such particular initial conditions in order to make our models work. But if you posit inflation, you kind of get a solution to these problems in the sense that so inflation just generally, it reverses that sort of dynamical evolution and drives things towards flatness rather than away from flatness. And it creates a way for things to be in causal contact in the past and spread apart far faster than they would if we just used standard kind of FLRW evolution. So what this does, in effect, is replace finely tuned initial conditions with some sort of dynamical explanation of their origin. Flatness comes about as a result of inflation. The thermal equilibrium of causally disconnected regions comes about because they actually weren't causally disconnected. There's just a mechanism that drives them apart. But if you posit, one thing I want to highlight here is that positing new dynamics, well, this provides a nice satisfactory explanation. If that explanation is true, you also need evidence that the explanation is true. You can't just posit new dynamics and get it can be a satisfying explanation, but it might not be the correct one unless you have some evidence that that's the correct story. So what's standardly kind of taken to be the evidence for inflation that tells us that we're on the right track is the power spectrum of temperature fluctuations in the cosmic microwave background. It's been covered in a bunch of talks. I want to point out that this isn't quite right. It's not that, so inflation provides a mechanism for those things, but it's not that inflation is what led us to predict that sort of spectrum. Back about 10 years before inflation was first posited, you have papers by Sunyaev and Seldovich and Peebles and Yu that basically kind of phenomenologically say, look at what we know about the distribution of large-scale structure in the universe today. If we evolve that back in time to the time of recombination, where the CMB is, they were able to figure out that the sort of distribution of anisotropies or density anisotropies in the early universe would have had to have been nearly scale invariant, sort of adiabatic temperature fluctuations, and they would have had to have occurred on super Hubble scales. And that would give you the correct, that's what you need to evolve forward to get the structure we have today. So you already have some sort of phenomenological account of what sort of structure, or what sort of structure we should see in the CMB independent of inflation. Of course, we didn't see that structure until much later, until we could actually make precise enough temperature measurements to see that structure, but you had some phenomenological account that must, in order to explain the structure that we observe kind of today, you have to postulate something like that occurs in the early universe. So what inflation does is not necessarily make that prediction, but it provides a mechanism for generating that nearly scale invariant spectrum of temperature fluctuations. So again, point here that inflation is an explanatory mechanism rather than making these. The one prediction that I think is clear that I've highlighted here is that it predicts that the scalar spectral index, so if the temperature fluctuations are exactly scale invariant, the scalar spectral index would be 1. Inflation tells you that it should be almost, but not exactly 1. And it's a model-dependent factor, whether that's almost but slightly above 1 or almost but slightly below 1. We currently favored models in the observational data says that it's slightly below 1. So in some sense, that's a correct prediction for inflation. It predicted a nearly but not exactly scale invariant spectrum for fluctuations. So that's something that inflation definitely has predicted. But original models of inflation that were kind of motivated by other high energy physics, so like Guth's model that's within grand unified theories or things like that, they got that maybe correct, but there was other issues, like you can't get the amplitudes for the power spectrum to fit. So that leads to postulating new models of inflation that have different background motivations, maybe connected to other areas of physics, or maybe disconnected from any high energy physics at all. And so that leads us to the shift from inflation as part of a theory to this sort of phenomenological framework or mechanism that's sort of theory independent in in some sense, or has multiple realizations. And what happens with this too is a sort of shift in the way we sort of test inflation. So if you have a particular model, the sort of standard scientific way, or like the naive scientific way, you have a model, it makes a prediction, you go and test that prediction. If it's right, the model's confirmed. If it's wrong, it's falsified. That's not what's happening here anymore. You have this sort of space of possible inflationary models that all make slightly different predictions. So for scalar field realizations, you have different shapes of the potential. You have large field versus small field, slow roll, etc. And all of these things have different impacts on the observational signatures in the CMB. And so this is a shift. Rather than going out and testing a model and then comparing it to the observational signatures, you're using those observational signatures to constrain this large space of models. So it's a shift in how we treat inflation. This is a graph from Planck data that I'm not going to go into the details, but basically the scalar spectral index and the tensor to scalar ratio are two parameters that are largely undetermined. They're sort of model dependent. In different models of inflation will give you different values. The gray, the red, and the blue circles, the blue one's kind of hard to see, are the sort of observational constraints, and then there's other graphs showing different classes of models, but basically you're using the observations to constrain the space of possible models, and so that's sort of an important shift. And so that's a shift to a mechanism of inflation, sort of independent of any theory, which in some sense is good. So if you have, from one perspective, you might think if we have good evidence that inflation happened, and we don't know anything about high energy physics, that's good that inflation is sort of robust or insensitive to those details of high energy physics. It kind of tells us that we're on the right track in some sense. But it can also be disappointing because you don't have any sort of higher level constraints for what the parameters are for inflation. And so one of the issues here, given that you're just sort of constraining parameter space, is that inflation is a flexible framework. There aren't a lot of, at the moment, observations that it needs to recover. So the scalar spectral index and the tensor to scalar ratio are the two big ones. But you basically, for scalar field realizations, you have, you can freely, sorry, if you're disconnected from any particular model of physics that's motivated by something else, you have a basically free potential function that you can tune if you want to get whatever predictions you need. You can also tune whether that you start out with the inflaton field at a very high mass, or sorry, high value or low value. There's a bunch of ways that you can tune the models. So you might worry a little bit that given what we want to recover, empirically, inflation is far too flexible of a framework that we can get almost anything we want out of it. This has led to, I'm sure if any of you have followed anything about inflation, you've heard about this debate that like kind of culminated in articles in the Scientific American, where you have Eos, Steinhardt, and Loeb criticizing inflation as being unscientific in some way, kind of for this very reason that I've just been talking about. It's such a flexible framework that it can never be falsified according to them, and according to them, that makes it unscientific. I think that misses the point. I think the flexibility is still an important concern, but I don't think that makes it unscientific. Then you have replies from, many people. The Scientific American article, I think, has like 35 authors or something on it that co-sign endorsing inflation. But I'm going to just say Guth et al. Because there's another paper, and he's, I think, the first listed author as well, where they sort of reply that we have great evidence for inflation. Inflation's already established in what we're doing. It's not that we're tuning the models to sort of fit observations, it's that we're using the observations to learn more about inflation. And I think that slightly mischaracterizes the point. As I was saying, I haven't really argued for this yet, but we don't necessarily have great evidence that inflation happened yet. It's a great convincing explanatory mechanism. We can use predictions to constrain parameter space. We have some crucial tests, which I'll get to towards the end of the talk. But I don't think we should be really that confident that inflation's been established yet. So while the terms of this debate, whether inflation is scientific or not, I think miss the point. There are interesting sort of things to look at in these papers. Those are the ones I want to highlight. There are some others as well. And so this kind of leads, so thinking about the physicists doing philosophy of science and arguing whether something is scientific or not, leads to step back and think about how do we assess a theory and its prospects. And there's sort of two I'm just splitting it arbitrarily into two. These don't cleanly separate. But when you first postulate a new theory or model, you don't have a lot of evidence for it. You can't argue whether it's been confirmed or whether it's secure or true or something like that. But you might be interested in its sort of initial prospects. Does it promise to do a lot? If it were true, if it worked out, would you learn a lot more about the world? Is it a feasible research program? Is there sort of ways forward you can foresee of how you might go test it? Does it make novel predictions, things that you wouldn't have otherwise thought of? Talk about explanatory depth, which Frozen mentioned as well in his talk. He's got a couple papers on that. Whether it's sort of worthy of pursuing further, all of these kind of fit into this sort of idea of initial prospects. But at some point, and it's not exactly clear where this kind of transitions, but in order for, as time goes on and more work is done on an initially promising sort of theory or framework, it's got to start to deliver on those promises. And sort of marks of long-term success, are some of those novel predictions, have they been confirmed, or are they, accommodated in some sense? Does it make decisive predictions that distinguish it from other competing research programs? Can you use that theory, assuming it's true, to then go discover new things? So for inflation, can we assume inflation and then learn more about the early universe and go and check that those things actually occur? Sort of at the strongest level, you might think that in a sort of maybe Kuhnian kind of sense that there's a really well-established theory sort of is conceptually necessary for even conceiving of how you do research in that field. That is clearly on the very strong end. But what I want to say is that inflation so far has scored quite high on the prospects. There's a lot of prospects for explanatory depth, maybe some novel predictions that might be quite hard to make. It's definitely worthy of pursuit. From a sociological standpoint, it's clearly won a lot of people over, so that in some sense it's been quite successful in that way. But I think it's lacking in some of these longer term successes. And one of the things I want to highlight in this talk is some ways that how that's deficient, what we might want, and how we could, what more we could do to help establish inflation and sort of shore up the long-term success. So just a quote from a physicist. I like to throw these in as a philosopher, depending on the audience, that I'm not just making things up. This is old, but I still think it holds, even with the new data coming in. Weinberg, back in 2008, kind of had mixed. He was both encouraged and discouraged by the sort of flexibility and success of inflation. So it says the consistency of models with of observations with a large class of models is encouraging because it supports the general idea of slow roll inflation, but also disappointing because it shows these observations don't really tell us anything specific about the details of inflation. With further improvements, we can look forward to more decisive tests. We have learned more, so it's not, it's a matter of degree, but I still think the point stands. We haven't really learned a lot about the specific physical details of inflation. Okay, so you might worry. There's sort of two ways that there's limitations here. There's sort of ones that are inherent maybe to the framework of inflation. There's something about the theory itself, or at least its current status, that's limiting it and stopping it from having long-term success. So some of these things, like I said, the flexibility might be an issue. The seeming independence from any sort of physical details might actually, while encouraging in some sense, might be discouraging in other senses. If it's not like helping us guide and discover new things about the early universe. So these are things that are problems with inflation, not just, as the framework itself. And I'm not saying those are like always going to be there, but that's one set of problems. Another set of problems is this idea that maybe just we have limitation of access. So this has nothing in particular to do with inflation. Maybe inflation is not to blame, but the early universe, 10 to the minus 35 seconds after the Big Bang, is really inaccessible to us. We have very limited access to the early universe. It's in the very remote past. The energies that we would need to be able to produce terrestrially to sort of recreate some of those conditions we're never going to be able to do, or to do at least any time in the foreseeable future. So maybe we could say, as a proponent of inflation, you might say, well, yeah, there's some issues with inflation, but you're demanding too much of it. It's really, theories of the early universe are going to be much more limited in a sort of empirical access. I think that's a point well taken for any possible theory of the early universe. But it's more fun to be critical, so I'm going to focus on these bits for now. Also because I think there's actually something we can do about these. We can address these concerns. The other set of concerns, it's contingent whether we can ever really address those. So two ways that you might go beyond phenomenology. One is to kind of go back to inflation's roots, re-embed inflation into a broader theory of high energy physics that makes several predictions in distinct domains. So the Guth's original model, I think, was a Higgs inflation in the context of a grand unified theory. So all of the bits of the grand unified theory are kind of, if you could test bits of it and those connect to the inflationary part, you can kind of get indirect confirmation by testing the theory as a whole. Unfortunately, that didn't actually work out. We now think grand unified theories are pretty heavily disfavored, but you could come up with other potential models of high energy physics and try to re-embed them that way. So that's one option. That option seems hard, maybe doesn't necessarily address some of the problems of accessibility. If we're dealing with an even higher energy physics theory, that might be even more inaccessible, so there's problems there. The second option, which is sort of much more, at least prima facie, appealing, is if we have some expectation that inflation is generic or decouples from high energy physics, we might be able to treat it as an effective field theory, and beyond just phenomenologically treating it as an effective field theory and using that as a parameterization, if we can sort of guarantee a robust sense of decoupling or have convincing arguments in favor of decoupling, we can use the whole machinery of effective field theory that's kind of used for quantum field theories generally now to sort of have a principled way of saying, of finding further physical details in terms of an EFT expansion. And so again, we can talk about this more in the Q&A. I have different thoughts about what an effective field theory is, or what I mean is a much stronger sense than what for us kind of outlined. So I'll get into that quickly, but by necessity I'll have to be brief. So just quickly, what I think are the sort of important parts for what an effective field theory is right now. I'm thinking of a fully quantum treatment. Think about it as like a quantum field theory with a built-in sort of upper limit on the energy scales at which it's applicable. It's well defined below those energies. It breaks down at that energy scale. That scale plays a central role in the theory. You might not need to know exactly what that scale is, but you need to include it, and you need to have some idea that you're dealing with energies well below that scale in order for the effective field theory to be applicable. For those of you that know quantum field theory well, it's basically the ordinary framework of quantum field theory with dropping the requirement of renormalizability and allowing for all possible non-renormalizable terms in your Lagrangian that are consistent with the symmetries in the chosen fields for that theory. And those non-renormalizable terms are all suppressed by powers of that cutoff scale. So as long as you're dealing with energy scales that are much smaller than that cutoff scale, those terms aren't going to contribute too much. And you can neglect them up to any order of precision that you want. And then you sort of determine the other coupling constants, the ones that are actually going to make a difference to the predictions you make at the energy scales you want, to the sensitivity you want. You take those couplings as sort of empirically determined inputs to the theory. And so what do you need to construct an effective field theory like this? First, you need to have some at least approximately well-defined, approximately stable notion of energy for the time scales and distance scales that you're using the effective field theory. You need that in order to have a separation of energy scales, that lambda that's demarcating the high energy degrees of freedom that you're excluding from the theory, the low energy degrees of freedom that you're including. You need to have at least, this is always fallible if you're dealing with bottom-up EFT and you don't know what's going on with the higher energies, but you need to have maybe some, at least, convincing arguments or thoughts that the high energy physics is going to be sufficiently well behaved. Maybe it's local enough. So string theory is the completion, for example. That's a non-local theory, but it's only non-local on the string scale, so you can, well below those energy scales, you can treat it as a fully local theory. Some sort of expectation like that might ensure that decoupling might happen. And one of the limitations of effective field theories is that you can only capture sort of low energy excitations to an otherwise stable, self-consistently determined background state. So often that's a vacuum state, it could be a thermal state, something along those lines. But the effective field theory treats small perturbations about that stable state. You can't deal with big non-perturbative effects in an effective field theory. So let's think about inflation and whether we can treat inflation as an effective field theory in this sense. I've got a couple criticisms here. I think I've roughly arranged them in increasing order of conceptual, things I find more conceptually worrying. So those first ones maybe are less worrying, and the ones at the end are more worrying. So the first thing you might worry about is that just by choosing to use an effective field theory construction, you're excluding candidate models for inflation, like the proposed concrete models of inflation that just consciously fall outside of the scope of effective theory. So effective field theory treatment has to have something like a relatively late onset for inflation. So you can't have, if you want to treat all of inflation as an effective field theory, it can't start at the Planck time, because then you have to include Planck scale physics, and that's well outside the range of any good effective field theory. So you have to at least only treat sort of later onset models, and only models that depend on where the crucial dynamics can be treated as small fluctuations. And small is, of course, relative to the energy scales you're concerned with, but things like chaotic inflation and eternal inflation, many of the models that fit in those into that framework just already are excluded from that. So eternal inflation models often depend on a sort of not like a tunneling effect to go both onset of inflation and ending of inflation. So you kind of tunnel out of a false vacuum, and that's a very non-small fluctuation relative to those energy scales. So you can only treat a subset of models. Faraz has a paper from a couple of years ago that is in studies, I think, that talks kind of qualitative philosophical discussion of some of the work that he was talking about today and earlier work, and he also talks about some of these limitations. So that's just, you're excluding some models, but that might be fine. Maybe those models, we should just rule those models out for other reasons. But. So another concern is how we justify what the background state is over which we're providing an EFT treatment. So in order to get the account of structure formation for inflation using cosmic perturbation theory, you have to assume that the background state is what's called the Bunch-Davies vacuum. It's like the vacuum state that's appropriate for de Sitter space, zero particle state for observers moving geodesically. And so one natural question is what justifies that choice of state? From a sort of qualitative, and actually some of the work that Faraz was just talking about, these cosmic no-hair conjectures, you might assume we have good reason to think that that's a justified state, at least after inflation's gone on for a little bit, as it drives away inhomogeneities and anisotropies. It might also drive away high energy excitations, so that might be a good choice of state if we're taking an effective field theory where we're not treating all of inflation, we just assume it's gone on for a little bit first. But if you want to treat the start, it still is a substantive assumption about what's going on in pre-inflationary physics. If you try to parameterize the high energy physics in different ways from just treating it as a vacuum state, you end up getting different predictions for structure formation. Inflation is sort of sensitive to these details of high energy physics. There's ways you can maybe turn that argument around that we can talk about later, I'm sure some of you have thought of. But anyway, there's at least this sort of question about how we justify that choice of background state, other than that we just need it to get the right calculations. And we can't really justify that choice from an EFT perspective because that choice itself is necessary for an EFT treatment. So you can't use effective field theory to justify it, except if you're just saying, well, it's getting the right answer, so therefore it must be right, which I can talk about later. But that leads to a more pressing, sort of more foundational concern that I think is essential to thinking about effective field theories in this sense, is a sort of guarantee of decoupling. should we expect inflation to decouple from high energy physics? So in a certain sense, whenever you're constructing an effective field theory from the bottom up, you run a risk that if you don't know what the high energy completion is, we could be wrong. The physics might not be such that it admits for a nice effective field theory treatment. So that's a sort of generic worry that I don't think, it's not what I'm worried too much about here. But even from within, just thinking about the physical context of inflation, especially the scalar field realizations, there's sort of internal worries that you might think decoupling will fail. So first is issues with scalar fields in effective field theory. We have issues of naturalness and the scalar field degrees of freedom, the mass and stuff like that are quite sensitive to the high energy physics. So this is a problem for the Higgs mass. It's a outstanding problem for effective field theories in the context of the standard model. If the inflaton is also a scalar field, it suffers from the same naturalness and decoupling issues. But a separate issue is also thinking about the spacetime setting for inflation. What you're doing, you have this very rapidly expanding spacetime. And the standard effective field theory treatments, you Fourier transform, high energies correspond to short distances. Things that are initially short distances at the onset of inflation will expand and become long distance, low energy things. It seems like inflation is sort of the exact opposite, at least at that level of a sort of framework you'd expect decoupling. You'd expect the things, really small scales, to actually have impacts at large scales. I'm going to skip that slide because I'm talking about inflation more specifically. So the worry here is what's called cutoff crossing here from this Burgess et al. Paper. So that's the part B here. So you initially, maybe at the onset of inflation, you set up your effective field theory. You have some physical cutoff scale. You exclude all the degrees of freedom that are above that cutoff scale. You include all the degrees of freedom that are below that cutoff energy scale. But as inflation goes on, the modes that were originally excluded from the theory become included, right? They expand out and they become relevant to your theory. And you can't just ignore that in your treatment of inflation, because this mode crossing, this cutoff crossing, is essential for how we actually describe structure formation. So it's those quantum fluctuations of the inflaton field. When they cross out in infrared at low energies, when they cross the Hubble scale, that's when they freeze out and classicalize and seed structure formation. So that's a really essential part of how we describe inflation. But it's actually really problematic at the UV scale, because now we're bringing in physics that we've tried to exclude and we think we are ignorant about, and it seems like it should have an impact. So this kind of relates to the vacuum issue, or the choice of justifying the vacuum state issue, because it turns out that if you assume that everything's nice and in its vacuum state at high energies as the modes cross into your effective theory treatment, then you can really control those effects. It doesn't have any measurable effect, but then again, that leads back to the assumption: should we expect that pre-inflation high energy modes were actually close to the vacuum? I think that you can make plausible arguments either way, but that's at least something you'd have to try to answer to address this issue of cutoff crossing. And again, different assumptions about how you parameterize that physics will lead to different predictions. In its most extreme form, this leads to the trans-Planckian problem. If inflation goes on for too long, if you take your cutoff to be the Planck scale, sub-Planckian physics that we know can't be treated as an effective field theory in any robust sense, that's the regime of quantum gravity. If inflation goes on long enough, not only do those cross into your sort of effective field theory treatment, but they might end up crossing in the IR and freezing out and seeding structure formation. And so this is it's known as a trans-Planckian problem, and you can, there's sort of ways to address this. On the one hand, if you're not super wedded to the effective field theory view, you might think this is a really great thing, because that would give us, potentially, if inflation goes on long enough, we have windows into weak signatures of quantum gravity, maybe by looking really precisely at the CMB. If quantum gravity effects actually do propagate out and help seed structure formation, we might see evidence of that in CMB. But if you want to hold on to effective field theories, you can kind of hand wave this away in some sense with a sort of ad hoc, what's been called the trans-Planckian censorship conjecture, where you just say, we're just going to put an upper limit on the duration of inflation to make sure that sub-Planckian modes never cross the Hubble radius. And so it's, at least at that level, the way I've described it is kind of ad hoc. There's been some recent literature on this conjecture and maybe using it as a constraint for constructing theories of quantum gravity, that maybe any good theory of quantum gravity will only allow realizations of inflation that go on for a certain amount of time. So Mike has a couple of papers on that. Interesting topic, but I'm going to set that aside for now. Cool. So quickly, why I don't think effective field theories work. You have these sort of internal technical problems with the effective field theory program. So justifying the vacuum state, excluding certain models. What I haven't addressed here, but I'll get back to later, is the eta problem, the sort of instability of plateau models, which are currently favored within the effective field theory approach. And then these sort of conceptual problems of decoupling and mode crossing, so that at least those would suggest that inflation can't really be screened off from high energy physics, at least not in a way that gives you this sort of robust systematic treatment. Yeah. So how else do we go then beyond the sort of phenomenology and just sort of thinking about testability or combinating the data? To recap, what we can do using just this sort of phenomenology is constrain theory space. We can use observations to constrain theory space, and that might then help us construct, it gives us constraints on what kind of models that realize inflation are allowable. So that might actually, long term, that's still a helpful goal if we can constrain the theory space. If we could then construct realistic models of inflation that are, that helps us build models that narrows the class of possible models by constraining that space. And then we get something like a how possibly explanation. I mentioned earlier that inflation is sort of one of its major appeals is a sort of explanatory mechanism. But if we just kind of then retreat to treating it as phenomenology, we're not really, it's maybe just the explanatory part loses a bit of force. It's maybe at best a how possibly explanation. Things we can't do. So we can't provide convincing arguments against the skeptic or against proponents of other models of structure formation in the early universe if we just stick to treating inflation as phenomenology. We can't really test or have much confidence in the assumptions that are common to the whole theory space of inflationary models, all of the structure that's shared by that model space. We need, by justifying that, I think we're already going beyond phenomenology. And of course, what we want at the end is a how actually explanation, ideally, of what happened in the early universe, not a how possibly. And again, at the end, we really want inflation to lead us down new avenues of research. A sort of fruitful theory suggests new sort of physical details or dynamics or effects to go look for and test, and going out and seeing those would give us a high degree of confidence in a sort of theory of inflation. I'm running low on time, so I'm just going to skip this. I said this earlier in the talk that I think that EOS and et al. And the Guth et al. Debate misses the point. So here's a quote that I have in almost every talk I give, if you listen to any of my talks. I'm a big fan of George Smith, who lays out in very clear detail this sort of methodology of what we want of a successful theory, a sort of mature theory, and how it gets confirmed in the context of Newtonian astronomy. He says what's important is not just that Newtonian astronomy can calculate the locations of the planets and their satellites, and that those calculations can be fit and agree with observations. But what really is essential here is whether discrepancies between the theory and what's observed help. The theory has the conceptual resources to kind of point out physical sources for why that discrepancy might be there, and then we can go and look for those physical sources, and that actually gives us the strongest evidence. So in the case of Newtonian astronomy, you have things like, we make very precise measurements of the orbits of the planets, and we see some anomalies with, Uranus's orbit, and we try to calculate all of the better approximations to things, and we still find that discrepancy, and so we think, okay, maybe there's some other gravitational body out there that's affecting Uranus. We find Neptune, we go look for it, we see it right where we expect it to be. That's a stunning confirmation. That's sort of the gold standard of what we want of a mature theory. We can even when it gets something wrong, we can then use it to find out something really physically robust in the world. So what does inflation need to get to that status? And again, with the caveat that the early universe is much harder to access than sort of the solar system, so this may be a long-term, far-off goal, but we'd want to be able to control the idealizations and physical assumptions that go into any specific model of inflation, and such that we can de-idealize when we see discrepancies between what we predict and what we observe. We want the theory, again, to play the sort of central conceptual role in guiding the search for new physics, like Newtonian astronomy did. You have to assume that the only interactions are gravitational and that gravitational bodies will mutually interact in order to sort of think, oh, there's another body out there that's influencing Uranus, and then to go look for it and see, find out exactly where it might be and then go look for it. So you want something similar for inflation. And again, going beyond the simple framing in the ES versus Guth debate of simple falsification or how scientific a theory it is, you want this sort of iteratively progressive research program that you start to learn more and more details the more precise you observe things, and you learn about new physical things that you wouldn't have otherwise discovered without using the theory. So those are all really long-term, far-off goals. I'm going to try to be a bit more pragmatic here. What can we do in the meantime? Ideally, the option would be, let's have a theory of quantum gravity that predicts all these things, and then we have this great explanation, but that might be really far off and really hard to test. So what can we do to push inflation along the way? And I'll quickly lay out a couple options, or many things that I think we should all of these things should be pursued, and the more further we can establish any of these things, the better off inflation is. So I think more effort should be put in to crucial tests of the assumptions that are common to the inflationary framework. So this has happened in the past, where there was this sort of competing model of structure formation that relied on topological defects in the universe. And it turns out that that is one case where inflation won out. Like classes of inflationary models generically make one set of predictions, the topological defect models make a different set of predictions generically, and inflation won out. So that's great. And I think we should keep doing that. Another example, so this is just one I know that was offhand, that Robert Brandenberger, for example, has this competing explanation that he calls string gas cosmology that's motivated by string theory. And one of the things that would be a decisive test between the two frameworks is that string gas cosmology generically predicts a sort of blue tilt of the gravitational wave spectrum, whereas inflation predicts a generic red tilt. So again, going out and looking for those sorts of things that consistently rule out, not just constrain the space of possible inflationary models, but test inflation versus completely different competing explanations. Another one is to have inflation be more like dark matter, as we discussed earlier today. Have this sort of overdetermination, have multiple independent lines of evidence, like consilience-style arguments, that even if there are only a few free parameters, if we have different ways to access those and measure those, or infer those from different sets of data, and they all converge on the same values, that's not necessarily testing inflation against competitors, but it's making a stronger empirical case through consilience or overdetermination. Another one is to shore up some of the issues with consistency with known physics. So this, I think, Fraz's work really addresses here, of thinking about the stability of inflationary solutions, as he talked about this morning. I think that's a great example of that sort of thing. But so again, there's sort of internal issues with the EFT framework. So the Eta problem, currently favored models of inflation involve a plateau-like potential. And if you want to treat it sort of within our known physical frameworks, like effective field theory, even just at a phenomenological level, a plateau potential is really hard to maintain in an effective field theory, because higher order corrections, like you kind of have that expansion of higher order terms. If you get a plateau generated to first order, the quantum corrections will generically ruin that plateau. So it's really hard to that's kind of like a tuning issue a little bit. And yeah, these other issues, again, that I said Fraz has talked about quite a bit, thinking about the attractor behavior for inflation, maybe solving just at a more general level, if we could solve naturalness problems for scalar fields within the EFT framework. I think, as I mentioned this morning as well, thinking about solving the cosmological constant problem, or having a way of excluding inflation from fitting into the cosmological constant problem. All of these things would help make inflation fit in better with our known physics, or what we'd expect from known physics. And again, model-specific realizations are a bit further off, having realistic models of the onset and of inflation, of reheating. Maybe you get further predictions from those specific realizations. Ultimately, you'd want some sort of physical candidate for the inflaton field. Maybe same thing with dark matter. We could hope to go and look for it via particle accelerators or whatever. And then finally, as I've hinted at a few times, is this really holy grail, is using the theory itself playing a constitutive role in guiding the discovery of new features of the early universe. If inflation doesn't just explain things we already see in the CMB, but inflation tells us that we should expect to see new things in the early universe, and we go out and find those things, that would be kind of the ultimate sort of holy grail, even if we don't have it embedded in a theory of high energy physics. Okay, so I'm over time, so this is the end. Major conclusions. I want to talk, if you take anything away from this talk, inflation has undergone a shift from where it's sort of now a phenomenological framework, and this sort of undermines the initial promise that it provides an explanatory mechanism for things we see in the early universe. We want to fill that out and make it more than just phenomenology, but I've argued that you can't do that just by appealing to the effective field theory framework, because generically we should kind of expect decoupling to fail, and that I think we can take small steps towards establishing inflation, some that are empirical and some that are conceptual foundation. Thanks.
Thank you very much. Now I'm facing a difficult task here, commenting on a paper with which I find myself in agreement. It would have been much easier if I could just point out, the 3 points or 7 points I disagree with. But let me raise 2 points anyway. One is more a question to you, asking for a bit more of information. And the second one, I'm going to try and play devil's advocate and undermine some of the things you said. So the first question is about the understanding of inflation as an EFT, in an EFT approach. And I'm not entirely sure whether the conclusion is of a stronger or a weaker form. The weaker form might be, well, we just don't have a guarantee that the high energy physics will be decoupled. Because, there are these internal technical problems, these external conceptual problems, as I think you called them at one point. And so we just don't know. Or is it, in fact, a stronger conclusion, saying like, no, actually we have positive reasons to think that it's not going to decouple from the high energy physics. And I think some of the things you said could be read in support of this stronger conclusion, like the mode crossing and in particular trans-Planckian problem. That might, of course, be a mechanism in which, the high energy physics, is not going to be separable from inflation. And for somebody like me, in working in the foundations of quantum gravity, I think that would be exciting for exactly the reasons you gave. And there might be sort of a quantum gravity signature in there somewhere. So that's the question. Maybe you can answer that. I don't know whether should they answer that now? And then I can
do that now if you want.
Okay, yeah.
Yeah, I think it's certainly the first for sure. But I think that's a sort of, in some sense, benign. We never, if we're dealing with standard models and effective field theory, we don't know what's beyond the standard model. We don't know if things will decouple properly, in some sense. I think I think that's obvious. It's a little stronger here. So I'm going to say that, just to fully answer the question, I am we have positive reasons to think it won't decouple, but those are also fallible. We could be wrong about that. But I think there are positive reasons. But I think, so one of the differences with the standard model and inflation is, even if we think we're right about the standard model decoupling from whatever comes next, namely because it makes a lot of predictions and it gets those predictions right. a lot of predictions, and that's the key. So like, if we constructed a standard model to predict a couple numbers, and we got those right, we might worry about the theory structure because there's this whole flexible framework to predict a few separate things. So one way, and similarly for inflation, we might say, well, we expect it to decouple because if we assume it decouples, it gets the predictions right. But again, I don't have like a counting argument for if it makes this many predictions, then it's good and otherwise not. But there's certainly some sense to which the more sort of independent things it can predict, or like otherwise independent if you didn't assume the theory, the more you can be assured of the more confidence you should have in the assumptions that go into setting it up. I think that's missing in inflation. So I think it's in one sense the weaker worry is still a little bit stronger than it would be for any other generic case of EFTs. And I've tried to argue that I think there are some positive reasons to expect that it wouldn't decouple, but those are fallible and that's controversial. Some people argue that there's this view that Faraz and I were talking about at lunch. There's sort of this, some people view inflation as sort of a Planck eraser because it just expands everything away, and any high energy, something like a cosmic O'Hare sort of conjecture, you'd think, oh, well, anything that was excited, it gets so spread away that it all just dies off. But then there's the other view of thinking of it as the trans-Planckian problem as a sort of Planck microscope. So that's not a settled debate. People have differences.
Oh, sure, yeah. Okay,
Can I
thank
add
you.
one thing? For some specific models, like the plateau models,
Could you use the microphone?
For some specific models like the plateau models, and this isn't original with us, obviously, this is a problem that's often discussed in the literature. This eta problem is, for those models, it doesn't look like the EFTs work. And so, but that's for a specific class of models, it's not for inflation quite broadly.
Good. Okay, that brings me to the second part, to the where I'm going to try and play devil's advocate. So you tell us that, I think that's a quote from one of your slides, inflation may be more firmly in place if the following basically 4 conditions are in place. First, if we had stronger empirical evidence for inflation. 2, if we had a tighter fit into a framework of known physics. 3, if inflation delivered a detailed physical description of the early universe. And 4, if it made completely new, unexpected sort of predictions, and that would lead to discoveries that couldn't be conceptualized without inflation. I think, duh. Yeah, of course, if we had these 4 things, this is not just putting it more firmly in place, then I think we would be talking about, Nobel Prizes and, who would get it and things like that. So there's a sense in which, if these things really would come, the long listing, if we get many of these elements, it's an established theory at that point. Now, with that in mind, let me go back to your dismissal of the Iyas et al. Versus Guth et al. Debate. I think what that can be used to say that you disagree with both, but not on the terms of the debate. Cutting through the rhetoric of whether the other guys are unscientific, but there's a sense in which you disagree with them that with Iyas et al. That inflation is not falsifiable. It is, but there could be some things which would make it falsifiable. For instance, if you would observe a blue tilt in the gravitational wave spectrum, favoring some string gas explanation over an inflationary explanation or something like that, that would be, so if the base parameters of the inflationary framework could be empirically undermined, then so it's not unfalsifiable against what Iyas et al. Say. But you also say against Guth et al., at least for now, it's certainly not the case that this is an established framework. It might be if, for instance, we would observe, I guess, a red tilt in the gravitational wave spectrum or something like that, and then it would be an established framework. So, yeah, I do think, so there's a sense in which I think you enter that scientific debate and you say, yes, that flexibility that we have in it is a problem, And we would need to reduce that flexibility and try and get a handle on what's going on fundamentally. But in a way, I think that's the same debate that, at least on one reading, Ias et al. And Guth et al. Are engaged in.
Yeah, go first.
Okay. So I think one thing that, so after hearing these debates over and over again, couched in a very sort of thin way about just, is it falsifiable? Like, did you predict the spectrum of perturbations or not? I think it's partly our frustration with that, and I think that same kind of narrow formulation is partly present in the Guth and EOS exchange. And so what I think we really want to do is say, like, there's an initial question, have you sort of re-explained what we already know about the early universe in a way that gives us a sort of consistent how possibly story? And what we want to say is, and then you go further from there. And what is it that you can say beyond that? That's the question. And also, is it possible to have further work done with the theory that you can see as further testing the theory? Can you think of the further work that you're doing as, in some sense, putting further empirical constraints on the basic ingredients of the theory? And I think that's the element of the debate that's the sort of thing that's missing from this debate. That you accept a theory, and then in the best case, as you're using the theory, you're sort of continually reevaluating it, in effect. And that just seems to not be something that they've sort of latched onto as an important further consideration. And yeah, so the things we articulate in some sense, well, duh, but they're kind of absent from this debate. So anyway, that's a motivating part of my response. But
yeah, I want to say too that so I tried to highlight, I was dismissive of the terms of the debate, but I tried to at least very briefly highlight the bits that I thought were important and that I take to heart. So I think the flexibility is an issue, and the constraining the parameter space is a sort of response to that, but not a full response. There are plenty of other things that, like talking about how likely inflation is from a pre-inflationary state. We had a whole question and answer period this morning about whether that's even a well-formed question, and that plays a really central role in the ES et al. Debate. So there's a lot of kind of what I would think of as red herrings that come up in that debate, and I tried to pick out the things that I think are important from that debate.
Yeah, good. Okay, thank you. That's very helpful. I think I agree with that. I think I share some frustration at the sort of superficiality and that's going on of some of that debate. But there's a way of thinking, beyond the surface of that debate, and then I think you get exactly to the questions you get. No, thank you very much.
Well, actually, I wanted to interject the conversation on this point because I have a couple of comments on this, reacting to what Chris Wüthrich said. So, with respect to the power the tilt in the power spectrum, so my understanding is that, unfortunately, in our standard model of cosmology, there are so many parameters that when you want to compute whether there is a red tilt or a blue tilt, well, you can adjust the parameters just to have one or the others. So there are so much uncertainty in these parameters that this cannot constrain different models, and in particular different models of the early universe, such as string cosmology or even loop quantum gravity for what matters, because the uncertainty in the cosmological model is, or the flexibility somehow of the cosmological model is so high. And with respect to inflation, another thing that comes to my mind is that we are when we wanted to test inflation and so on, and then, well, there are issues of consistency with all the other things that we know, and the issue of the Transplanckian modes, I think this is quite central in the sense that this is not an issue of quantum gravity, because the absence of Transplanckian modes is something that is not specific of just loop quantum gravity or just string theory. I think this is something that should be a shared knowledge from the physics we know, and yet in the community, people are trying to invent solutions to keep inflation and have Transplanckian modes. So it's really a matter of how we proceed and which part of the theory we trust and why we keep on keeping certain parts when they are in contrast with the rest of our knowledge.
Yeah, I think that's a good point. I think this kind of relates to the sort of framing of like initial versus long-term prospects. And I don't have, I would say if I had to bet money on any early universe scenario, I still think I'd bet inflation. So I don't want to paint the picture that I'm too pessimistic, but I think there is some worry that, 40 years of quite a bit of work, foundational work on inflation has led to, and I think this is also something that's right in the EOS criticism, has led to some not increasingly refined knowledge, but almost like a shifting in what the goal is, from rather than model-specific realizations to constraining, assuming something like inflation happens and constraining that parameter space. And so I agree that, there's some potential worries about these may be sociological, they may, I focus more on the philosophical stuff, but they, what I think a more negative or a more pessimistic version of my talk could have been, why are we still holding on to inflation, but I'm not going to push that.
Oh, Chris first.
Can I ask a question, Francesca? So you think that the blue tilt in the gravitational wave spectrum would not be a problem for the inflationary framework? So you seem to say that there's so much flexibility.
No, what I'm saying is, I'm saying that the prediction is clear, but the measurements are not, because when you interpret the measurements, you have to plug many parameters. So it's not just a single measurement, it's that you plug so many different parameters in order to extract whether there is a blue tilt or a red tilt. And what I gather from people who are more into working with data than me is that you can get one thing or the other just by rearranging these parameters. So we are not, even though we speak about precision cosmology and so on, we are not in a situation in which, so the model is getting more and more complicated, and we have to be careful. Again, it's something that, the same thing that we were saying before, we put constraints on our theories. With data, we have to be careful of what inputs we put in order to extract this data. This is what I'm saying. But I had the conversation about this maybe some 10 years ago, and I don't know if the situation is improving. First hands is there. Farad.
Okay, thank you, Adam, very much. I have a number of questions. I don't know where to start, but maybe I'll start with this. So you had a description of EFTs, like a definition at some level of what is an EFT. And I was wondering to what extent that description excludes bottom-up effective field theories generally. I think this is something I was hoping to get clear on. Yeah.
So I think this bit, and maybe what you think about as excluding bottom-up EFTs, I don't think, so I tried to say in the talk a bit more that there's like some reasonable expectation that things decouple is important. So like I think you can treat the standard model as an effective field theory, like standard model particle physics as an effective field theory, despite the fact that we don't know what's beyond it. So I think that, barring issues with the Higgs mass, I think that's still an issue. But more or less, you can treat it as a. So I don't want to. If anything came across as excluding bottom-up EFTs, I don't mean to.
I see. Okay. Okay. So can I ask a follow-up to this? So this was all done in the context of canonical single scalar field models. And I was wondering to what degree the kinds of problems that you're describing for EFTs of inflation, understood as sort of phenomenological characterizations, to what extent do those problems go away if I think of the dynamics as being controlled by a single clock as opposed to a single scalar field. And,
Yeah, so I think.
oh, sorry, yeah.
Oh, go ahead.
Oh, just part of the motivation for the question is just that there's a kind of agnosticism, a very strong agnosticism, I think, that is imposed by a single clock or included by a single clock that, that you could say is not true of something like a canonical single scalar field model.
Yeah, so yeah, I think that's a good point. I agree that I tried to flag that I couch everything in terms of scalar field models because that's kind of what's standardly talked about. I think some of these problems, at least, I don't know if I don't know enough about the details to know if they completely go away. They would definitely change form, like the eta problem, that's a problem that's kind of, just described in terms of the shape of a potential for a scalar field. So obviously, even if that exists at all, it would have to change form drastically. So I think a lot of those internal problems might go away, or at least significantly change form. I'm still pretty concerned about mode crossing and that sort of decoupling, something like a trans-Planckian problem. Regardless of whether it's a scalar field or not, you still have this issue of whatever you're excluding from the EFT leaking into it at later times. So, yeah,
And I have just a question. I've always thought of some of the ways of treating inflation as an EFT as being really explicitly only phenomenological. And I've thought of the single clock formalism as obscuring the possible connection with the underlying particle physics theory, or just sort of setting that question aside to some extent. So so we might just be willing to say, yeah, there's different ways of writing down EFTs for inflation. Some of them make it less clear how it would relate to an underlying particle physics model, and that's, from our point of view, not necessarily a virtue. I don't know if it might lead to a different perspective on the technical problems we've indicated with regard to its limitations as an EFT, but I don't know that it addresses the further question, which is, let's say you have that single clock formalism and you've described structure formation in that framework in a way that matches all observations. I think our worries about how you go on from there if you merely have a phenomenological framework would arise, even if some of the technical considerations are slightly different.
Right.
But I don't really have, so as part of the question, is that the right way of thinking about the single clock formula?
So here's another way of thinking about it, which is sort of a complement to what you're saying, that if it's the case that, I think the single clock formalism was developed in part to address the fact that we don't have a sense of what the actual higher energy degrees of freedom might be, and to treat all possibilities under one umbrella. And so the benefit of that is that if you in fact find a prediction of a single clock formalism that is not borne out observationally, you've now discounted an entire class of ways of realizing the dynamics of the very old universe. So that's a positive spin on the same sort of issue.
Okay, so I have questions from Mike, Nick, and Sean.
Right, so as you won't be surprised, I'm immensely enthusiastic about a large swath of this project. I also like that the Closing the Loop got a responsible treatment, because tomorrow morning I'm going to give an idiosyncratic, my own version of it, and I was going to be irresponsible by not actually getting the words on there. On brand. The thing that I wanted to push on, just to hear the reaction, is how much work is being done in the back of your mind on this project by that promissory versus eventually the thing's got to have some justificatory weight. And the reason why I'm asking this is because some of the phenomenological approach mindset, certainly the bottom-up constraint on quantum gravity type mindset, is kind of made from a mentality of being permanently in the promissory state and thinking that there's some sort of artificial splitting off of the eventually it needs to acquire justification. And here's roughly the motivating thought. There's something almost unfair in the contingent history of the development of theories, which is that some initially promising things realize the initial promise very rapidly, and so it doesn't matter, it never comes to pass that they're not the sort of thing that can acquire justificatory weight. And you might think that other things just contingently don't realize the promise very quickly, nor are they well suited to get justificatory weight ever, but somehow they're still alive and they're still brimming with promise at every moment into the future. And so I think to some extent that is in the background of some of the embrace of inflation in various different ways by different parties, that it's perpetually still as promising as it ever was. And so, yeah.
Yeah, so I think in terms of so one way, a weaker way of framing it than you just did is, maybe it's a long ways off from delivering on its promise, but rather than saying, and maybe it's not the sort of thing that ever will deliver on its promise, but we hope it eventually will. And so, there's, was it Feyerabend that talked about this principle of tenacity, and I think that's perfectly fine in terms of wanting to develop certain research programs and things like that. And my goal is not to prescribe what physicists should or shouldn't be working on, except for maybe thinking, if you want to confirm inflation, these are some things to maybe focus on. But so I'm totally fine with that sort of approach. I am skeptical of the idea that it's something that, despite not delivering on promise, or maybe not really ever being able to deliver on promise in the way you kind of formulated, is nevertheless still as promising. I don't have a very well-formed thought on this, but I would think my sort of background thought that's in it is the more, I think of if I promise to give you $5 at some undetermined time in the future, and 100 years from now you're still really excited to get that $5 from me, I'd say you've probably, you're not behaving rationally in some sense. Yeah, he said he would, so maybe I'm just not that trustworthy of a guy. And so I think, I don't want to characterize any particular people's approaches to working on inflation, but I think if they were to say themselves that it's not the sort of thing that we expect to ever really get sort of this heavy justificatory weight, and nevertheless, after 40 years, it's still just as promising as ever, or maybe after 100 years, it's still just as promising as ever, I would have to disagree with that. I don't have a good argument off the top of my head for why I would disagree with that, other than I just think that sort of part of the promise is that it will, there's sort of promissory note that it will deliver on some of the prospects. And insofar as it doesn't, then it should kind of be discounted over time.
So I'll just submit this as food for thought, I guess. To what extent is the instinct here actually some sort of realist commitment that what promise means, how we should interpret the promise of a thing, is that it will eventually transition to some sort of richly justified, robust account of how, say, the early universe is on the way to even earlier in the universe and so on. Because this idea that the $5 100 years from now, right, is I think the intuition being pumped here is that promise is eventually supposed to convert, as opposed to some sort of pursuit worthiness account that there's just something about it that lends itself to creative theorizing entirely. It's a good tool to use to get ideas flowing. And
yeah, so I think framed that way, I think that's kind of, you've got the right idea that I'm thinking about. I don't know if I quite say it has to be cashed out in realist terms, but it's definitely amenable to that it's got to sort of deliver in some sense. I don't think there's a hard shift where you can say in 1772 Newtonian astronomy made that shift or something like that. But it's a transition over time. It's not a clean separation, but something along those lines.
Okay, I think with the time we are shifting into the discussion time, but I have Nick, Sean, and Katie in the line, and I think we can use this time for.
We moved on. It's okay.
Yeah.
So
We moved. It's not relevant now.
Yeah, but okay, you moved on. Okay, so Sean or Katie? Katie first.
Just responding to the point about why inflation continues to be promising. I mean, my argument would just be that we don't have anything better, right? All we can really do with these kinds of models is compare them to other models, and all the other models. There are a couple of other models, and my PhD advisor is Paul Steinhardt. He's got his model. There's, other people working on interesting alternatives, but they're they're just not as formed yet, and they might have better sort of underlying fundamental physical basis eventually. That's kind of the point of these alternatives, is to be more bottom up, and to try to reproduce the successes of inflation. But at the moment, inflation works, and nothing else is really there to work with. So I would say that until we have something better, I'm not sure what else we can do.
Yeah, completely agree with that. One point that I may bring up that maybe, I don't know, Chris might have been just about to interject this. I think that's also really true. I think there's an interesting sort of both sociological and like social philosophy division of labor sort of things that we could think about, and that you might argue, I'm saying one might argue, I'm not saying I do, but one might argue that perhaps some of this more critical look I've taken at inflation should motivate a redistribution. Inflation is the best we have right now, and it's also by far the most developed of all the alternatives we have right now. So it's hard to say. I mean, I don't make any endorsements about any particular model, but perhaps there is one that's a better bet, and it's just nobody's focusing on it because everybody is focused on inflation.
Well, I think at the moment there are so many models of inflation that I think people choose the one that they think is most likely to lead to an interesting sort of fundamental physical basis or observational test, and they go with those. So there's branching happening away from kind of standard inflationary cosmologies, but not all the branching is scrapping inflation entirely, and maybe there should be a distribution that's different. I'm not sure, but
yeah, I wouldn't know how to exactly answer that question, but I think that's an interesting sort of thought to think.
Thank you so much. I suggest that we take a 5 minutes break to stretch our legs and get some more coffee, and we reconvene for the discussion. But first, let's thank Adam and Chris.